So it's like 10 times 3. Okay, what is the question? The question is, I guess you have this grid. You see the okay, so you have an n by n grid. Let's do like n equals like 7. Let's see. Okay, n equals 7. And so like you have counter. You have counter. There's one counter in the top left corner. Okay, and then you just play this game where basically you're allowed to make this move. You're allowed to place a counter in a square if the square is not occupied already by a counter, and also the number of counters already in the row plus the number of counters already in the column is odd. So for example, I can place a counter over here because before I placed it, the row it was in had like had one counter and then the column had like 0. And that's allowed because 1 plus 0 is odd.
Where does the first
And so
counter
yeah, I
have
guess
to
you
go?
keep so you're basically just given that there's one counter in the top left, I guess.
Oh, you're giving it in the top left. Okay.
Yeah, you just get this one counter and you kind of just have to build on that. So you just keep placing stuff, I guess. Like yeah, I don't know, maybe.
Counter attack.
Yeah, I don't know. You can just do a bunch of stuff. But yeah, that's basically the problem. And the question is that like how many counters can you get on the board at most? Or like how many counters can you leave? How many counters have to be empty, I guess. At least how many spots on the board don't have counters? But I guess it's easier to just say how at most how many counters can you place? Because that's like less counters to state. So yeah. I guess the first thing to do is just like try small case. Let's do 2 by 2. I think 1 by 1's just like dumb. So just put one counter there. And then that's literally already the whole board's filled. So because we'll just like say n equals 1, where n is the side length. We'll just say like one counter. Okay, what about n equals 2? So we'll log you place the counter here. And then you can log again, you place the counter here. And you can't place it here because this is even. So n equals 2 is 3 counters. N equals 3. Let's see. It's pretty interesting. No, that's 4. So if you get n equals 3, not sure what I did exactly, but like I place a counter here, and then here, and try like here maybe. I don't know. Yeah, here's legal. Okay, so now I place something like this. Here, that's legal. And then this has three, so that's illegal as well. And then this has 3 as well. And now we can't place anything because of 1, 2, 3, 4, 1, 2, 3, 4. So I guess after you try a bit, you get kind of convinced that it's that you can get 7. Okay, so what is okay? So I guess the problem is like, what is the pattern, right? We can't really see right now. Because the question was asking how many can you leave empty? So I guess so I guess what that answer would be like 0 empty. And then here that would be like 1 square empty, and then here that would be like 2 squares. They're like, oh, what if n equals 4 is 3? What if n equals 4 is 3? Okay, it's not. So I guess that's one hard thing about this combi question is that it's just like what is the pattern? Yeah, so it turns out I guess that for n equals 4 you can sort of okay, let's just log we do these two. I think what did I do? So I did like Not exactly sure. Okay. So I basically placed these two counters at the top, and I went like this one, this one, this one, this one. I think something like that. And then what I did was I kind of reached the bottom, right? So I place one here, place one here, 1, 2, 3, 4, 5. I can place one here, and I can place one over here because it's 1, 2, 3. Okay, and then I noticed that I'm kind of in the same situation that I was in before. So remember at the beginning I had two counters over here. Now I kind of just have two counters over here, so it's like a new 2 by n column, I guess. So I just repeated the process. I did this, 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 and notice why can I repeat the process? That is the question. Okay, so pretty much I basically have this 2 by 4 rectangle already filled, and so the idea is that this filled rectangle, it contributes an even number of counters to every single row and column, meaning that I can practically disregard it because it's not going to change the parity of the rows and columns. So yeah, I just ignored everything here and I just focused on this, and I can actually do the exact same thing for this to like this weird pattern to fill these ones, and then I can fill one last one, 1, 2, 3, 4, 5, and I realized, oh shoot, I can't fill anymore. So obviously you cannot fill the last square because the last square, if there's one last square left, then there's going to be the same number of counters in its row and column, so that's going to be even. So it's impossible to fill everything. So n equals 4 is like 15 counters. And then there's 1. I don't know. But yeah, and so now I'm beginning to suspect that I can get 1 remaining in a lot more than just 1, 2, 3, and 4. So I guess maybe I can expand this pattern to something a little bit bigger, right? So let's try like an 8 by 8 just to have, I don't know, maybe extend the idea that I already used. Okay, so now I have 1 counter at the top. Now I do the same thing I did before with the 4 by 4 grid, I guess. Except this time I like, okay, I'll just start out with the same where I place like this, 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 and then this. So now I have a 2 by 3, but then I realized, I can actually repeat this. So I can just go like this again. And then just keep going until I reach the bottom. And once again, I'm at the bottom, but then I can do the same thing I did in the 4 case where I did this. Now I have a 2 by 8 column that's completely filled. I can disregard it because it contributes even numbers to every row and column. So now I just like do that again. And you get the idea. Yeah, I don't know. Yeah, okay. You get the idea. So I kind of just zigzag up and down the board by using this pattern of like, I have 2 at the top, and then I do this thing called like 1, 2, 3, 4. Like I kind of just do this sort of pattern of placing counters, and the reason it works is because like originally when I haven't placed any, I'm basically just going to assume that there's an odd number of there's an odd number of counters in the columns, but then even in the rows. And when I place the first 1, it's going to be in an odd and even, so that's going to be odd. Same with the 2, that's going to be odd and even. But then when I place the 3, wait, I'm not sure. Wait, did I place it correctly? Oh yeah, okay. So and then when I place the 3, it's odd and even, but because I added the 1 and 2, this one becomes odd and this one becomes even. So it's actually fine. And then same with this one. So basically I just tile this pattern of placing the counters down, and then I do this, and at the bottom I do this pattern of going 1, 2, 3, 4. And so what that does is just creates this 2 by 1 thing that I can then reuse over and over again until I get to the end. So I guess that's the construction for evens. I can actually get yeah. I can actually get everything except one. So for odd, I guess it's a little bit difficult because this will try the 5x5. You see, the thing is, I didn't get this in the exam, so I'm not exactly sure how you would motivate your answer for odd case. And the odd case is definitely harder. Let's do a 5x5 real quick. So I think I don't know. This is inspired by what Yang said after the exam, how he did it. But basically, his idea was basically to use induction. So pretty much we already know how to do 3x3. So let's just place a 3x3 like this. And I guess the claim is that for odd, the answer is that you have to leave n minus 1 empty. So how do you get n minus 1? So I guess you can place one here because there's like an odd number in here. And then for the rest of these, yeah, so you can place one here and then place one here and then here and then here. And then yeah, that works. Okay. So after you do that, you kind of move on here, I think. And then 1, 2, 3, 1. And then I go up. And then this way. And then this way. And then I fill in this one. I believe 1, 2, 3, 1, 2, 3, 4. Yeah, okay. And then over here I kind of place the same thing. That yeah, like this, and then 1, 2, 3, 1, 2, 3, 4. Okay, so now I've basically achieved only 4 empty squares in 5. So just how can we turn this into an actual induction where I fill in the squares accordingly? So I guess the induction hypothesis is for this assume n odd works. You can achieve n minus 1 empty. Okay, now we do n plus 2. The n plus 2. So basically what you do is you have this n this. So in the induction step, you basically want the empty squares to be along this diagonal. Sort of like this in the n construction, and then so they're kind of like that. So these are the empty squares here. But there isn't an empty square in the top left. That's the only square along the diagonal that is not empty. So what you do is you place a counter here. And then because okay, so notice how this in this square, because the ones on this diagonal are empty, pretty much these columns and the rows, they have an even number of counters already in them because it's odd, but then there's one missing. So then I can place one here because this guy is already here, so even plus odd. And I believe that I can do this as well, because then there's even plus odd here. And then I can sort of move over here and do that. Because there's only one in this row, and then this is even. Okay, and then I can do this one again, because I'm gonna assume that this has an even number, and then this is odd because it's this even plus this one. So and I kind of just squiggle my way over. I believe so. It's like, yeah, just squiggle my way over. Okay, but now I can't squiggle anymore because I actually want this to be empty. I want this one to be empty, so instead I think I go here because I've filled basically I've filled n dots in this row and there's nothing here. And n is odd, so I can do that. And then I go up one. So obviously I can do that. And then I go left. And then I go down here. So because there's this missing dot over here, there's an even number of them in this row. But then because I have this extra dot, then I can place one here because that makes it odd. Also, this one's supposed to be empty. That's our goal. And then because we have an odd number here, because it's like this even plus the odd, and then hold on, I need to check this. It's very confusing. Okay. Yeah. Oh, let me just check on the 5Ks because I'm a little bit confused. So what did I do? Okay, I'm gonna do something that doesn't really make sense yet to check it, but it'll make sense eventually. I'll do this. Yeah, okay, so I see. Okay. So yeah, the point is that there is an odd number over here because it's like basically this square but shifted over. Then there's an even number over here because there's this odd number plus this one. I can do that. And then here, I basically done like 1/2 of it using this method. And then I just need to fill in this remaining rectangle, which is actually pretty simple. I basically just do the same thing, same sort of squiggle pattern, I believe. So how does this work? Let me check. Yeah, so basically there's these two over here, so there's an even number of things in these two columns, which means I can just disregard these guys and then only focus on this square. So I just do this. I think, yeah. Do that, and then that. It's like squiggly. Some weird squiggle thing. And then eventually I think I can do, because this is once again an odd number. And then this is even number because it's called this extra dot here. I can fill in this. So that's the construction for odd. It's basically induction. So basically you just construct this so for n you construct this the induction hypothesis construction in this top left, and then you do this squiggle thing, boom 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 boom, you go up here and then fill in that, and then you do squiggle on this side again, and then that's, I guess that works. Okay, so I think the hard part of this problem is realizing that you can't get better than n-1 because you have the construction, but you always think like, what if there is a way to get like 2 empty or something? Well, it turns out there's not a way. This problem's actually probably supposed to be pretty easy problem, but I think like something happens with Combi problems in exams that for some reason like everyone just dies. So how do we prove that these are the limit? Like you can only get so many counters on the board. So the problem is like, okay, so the even case is really easy because the even case, you can get everything except for 1, and obviously you can't do the last one because there's an even number of it in the row, so you can't fill in the last because there's the same number of counters. But what about odd? So here's an interesting observation. So I guess if you look at the question, what you really want to keep track of, and kind of what I did here, so like this will make sense now that I explained this, is that if you sort of keep track of the number of counters in each row and each column, this is very useful information because that's basically all you need to know whether you can place a counter in a specific spot or not. Right. So for example, like there's like one counter in this row or this column. And actually you don't even need to keep track of the number. You can simply keep track of whether it's odd or even, right? So initially you start with this column has an odd number of counters in it, and this row has an odd number of counters in it. And based on that, you can basically conclude that all of these squares you can place counters in, and all of these squares you can place counters in, because they have like an odd plus an even number of counters in the rows and column. So now notice what happens when you place a counter, right? So I guess when you place a counter, you're basically toggling the parity of the number of the counters in its row and its column. So say I place a counter here, right? So what changes does that make to the row and the column? Well, basically, since this row was already odd, it's now even. And since this column was already even, it's now odd. So that's pretty cool, right? Because you're basically able to keep track of where you can place counters without actually keeping track of the counters themselves. Because you just have to look at the parity of the row, and every time you place a counter, you just toggle that row from odd to even or vice versa. Okay, but here's the interesting thing, and this is what I was doing earlier when checking the 5x5 case to figure out the construction. So here's the interesting thing. Notice how, because there needs to be an odd number already in the rows plus the columns, right? So row plus column equals odd. That means that one of them is odd and one of them is even, right? So either the row's odd or the column's even, or the column's odd and the row's even. So what does that mean when I place this counter, right? So you can see that when I place this counter, the rows was odd and the column was even, but now the row is even and the and the column is now odd. Okay, so what does this mean, right? I've taken away an odd column, an odd row and made it even, but then I've also introduced a new odd column from its previously even state. This is actually an invariant problem. Holy crap. And the invariant is that there's always two rows / columns that have odd numbers of counters in. Because every time you make a move, you're basically just toggling the stuff that it's in, and one of them's odd and one of them's even. So you're just moving where the odd is, right? So from now on, I'm not gonna even mark which ones are even. I'm only gonna mark which ones are odd using this weird dot notation that I just did beforehand. Like these dots just mean that this row is odd and this column is odd. And then whenever you place a counter, it basically, you have to place a counter in a square where the row where only one of these dots appears, because that means it's odd. But then when you end up placing the counter, it just switches that odd from row to column and vice versa. So now I know I can place a counter, say here, but then it would switch this dot from here to here, and then I can also place one here, but then I'll switch it over. Okay, but enough of that. That was basically what I was doing when checking the 5x5 cases. If you make this observation early, it actually makes it way easier to figure out the construction, because now you have a really easy way of counting things. You do not need to count the dots every single time. You can just use 2 dots to figure out whether you can place it or not. Let's take a look at the even case. So the even case, we already kind of proved that that it's not possible to get all of them, that you must have an empty square at the end. But let's take a look at like odd case. So the special thing about the odd case is that because I guess let's see. So because there's two rows slash columns, so let's write the invariant down. Two rows slash columns that are odd. Because there's two of them, that means the rest of them are even. And because we're looking at the odd case, this means that those rows, all of those rows slash columns that are even, they have to have one missing, right? So that's pretty interesting. So if you have an n by n grid, and then n is odd, then you pretty much have like, so there's 2n rows and columns in total. You pretty much have 2n minus 2 rows slash columns with one missing. One counter missing. At least. And that's already looking promising because 2n minus 2 is twice n minus 1. So I guess, yeah. So I guess if you assign to each of those empty squares a row and a column, you already have this exact condition. But now let's just do the actual proof part, which is the thing you write in the exam, which is, I guess, proving that because of this condition, you have to have at least n minus 1 empty. So I guess to prove that, we'll do the contrapositive. I think, I don't know, is it the contrapositive, which is that what if there is less than n minus 1 that n minus 1 squares that are empty. So let's say there's like n minus 2 or less. So if you just have a bunch of squares that are empty, right? Like just a bunch of them. Each of them occupies one row and one column. So if there are k empty squares, since they occupy one row and one column, this means that they can together, they have to occupy at most occupy 2k columns slash rows. So these empty squares are in at most 2k columns slash rows. The thing is, they can overlap, right? That's why we say at most, because obviously, like these two empty squares say they're like in the same one. So I guess we don't count that, but it is at most. So let's say that k was less than n minus 1. That would mean that 2k would be less than 2n minus 2. And of course, we know that empty columns slash rows, columns slash rows with empty is less than 2 or equal to 2k, which is less than 2n minus 2. But we have already established that there must be 2n minus 2 rows slash columns with at least one counter missing. So that's a contradiction. So that's basically it. Yeah. So I guess, I don't know. I guess this problem was kind of meant to be easy, probably from the AMT standpoint, or at least like whoever made this question, because the invariant is relatively simple. It's literally just like how many rows and columns are odd. So that's very simple to observe. But I think not many people got it, firstly, because too busy working out the bound, right? So you need to be very busy working out a construction for the even case, and also, oh yeah, by the way, this invariant thing, I believe the invariant can be also used to prove the even case simultaneously. That there has to be one missing, but I don't think that it's really necessary to show that because it's pretty obvious that there has to be one missing. Yeah, in the exam, you'd be really busy trying to find the construction. So firstly, the even construction you can find. The odd construction was very difficult to find because it's like some weird induction with some crap happening. I don't know. It's pretty difficult to find. And then once you're done with that, now your brain's like completely dead. And then you have to, and you're not even sure that your odd bound's correct. And now you have to find a proof. And now it's just impossible. Because you're brain dead already. So I guess that's why a lot of people didn't solve question 4, because it's just that the bound's pretty weird. And yeah, and by then you wouldn't be able to notice the invariant. And also I probably contributing to this is just like people couldn't do Q3. I don't know. Q3, yeah, I guess it was pretty hard. Like not many people, like a lot of people died. So yeah. But yeah, that's it. But yeah, that's basically Q4. It's literally just one invariant. But I feel like if you notice the invariant at the very beginning, then you'd basically be done. But of course, the natural thing is to start trying small cases and then yeah, and then find the bound. But that's so much harder because by the end of that you can't really think of like. But yeah, that's basically
You guys have any questions? That was a really awesome presentation. See how clear that was? That was very clear. Yeah, so the n-1 follows completely from that, just having the 2 dots somewhere along the row or column. Is that what you're saying? Just
n-2.
n-1.
Two n-.
Yeah. So like if the 2,
yeah. Yeah. Yeah, this is weird because like this is like one of those questions where like if you're big brain at the beginning, then I guess you're done very fast. But then if you do it like the normal way where like you just try stuff and then figure it out, it's gonna take a long time. And I think not many people had that much time, to be honest.
Yeah, but the time
question 1 was okay. Question 1, I don't know what people's experiences were with it, but yeah, it was a little bit shaky because I guess for me, I had to find the exact example that would prove it. So question 1 was easy, but by no means trivial. Question 2, I actually made a mistake on it. So that was like, I guess that indicates that it's not that easy. It also, okay, firstly, it appears as a game theory problem, and then you realize, oh shoot, it's number theory. And then the solution is quite simple, but question 2, I guess it's like when you haven't solved it, it's really scary. It actually took me like an hour to do, which is pretty sad. But yeah, so that question was pretty scary, even though the solution was easy. But and then question 3, of course, I think just actually I don't know. Yeah, question 3 was just I don't know, something happened.
Yeah.
I guess it makes sense.
How long did it take? How long did it take you to do question 3?
Question 3, I don't know. Like, how long did it take me to do? I don't think it took me that long.
Okay.
Like once I actually started doing it, like I looked at it while doing question 2 because I was scared. But then when I actually started doing it, it just came. I don't know. And maybe it took me like 5-10 minutes to think of, and then writing it up took a bit longer, but yeah, it didn't take that long for me. But question 4, man, I think I had like 2 hours. 2 hours to do question 4? I don't know. I'm not sure. Maybe a little less. But unfortunately, by then, brain not work. And this one's the big brain problem. So,
all right. Thanks, Alex. That was good.
Pretty interesting ASC. Yeah.
Very good.